define the sub-equivalence relation as a Cuntz order. A is Cuntz below B if and only if there exists a sequence xn in your algebra A such that xn star b xn tends to A. There are several variants of this relation. This one is the most common now. It seems to be the best behaved one. Okay, and once you have this Cuntz order, you can define equivalence of positive elements. A is Cuntz equivalent to B if and only if you have A is Cuntz below B and B is Cuntz below A. Okay, that's an equivalence relation, and you can use that to define the analog of non-stable K-series, so to speak. So you define the Cuntz semigroup. Let's define that in the 70s. I think it was 1977 or so, around that time. You define that as follows. You take the following WA is defined to be the positive infinite matrices. Once you do this relation with up there, which makes sense also in this algebra here, you can use it in all matrix algebras, and you have there a direct sum operation which gives you the sum in your semigroup. And then there's also another version which recently featured, which is CUA. There you take A tensor K, the compact operators, plus modulo that sub-equivalence relation. That's somewhat better behaved than the inductive limit, but you have to reinterpret actually what an inductive limit should be to change the category a little bit. Okay, so just to get a little bit of a feel for this, there's some standard examples. So the first example, the easiest would be perhaps that A is T of x, where x is a compact space, although you can also take C0x for a locally compact space. Then if you have positive elements in there, functions now, f and g, and f is Cuntz below g, that will be the case if and only if the open support of f is contained in the open support of g. By open support, we just mean those points where this is strictly positive. Your function is strictly positive. Okay, so then in this moment, basically the classes you look at are the Cuntz classes, which you would take here, are classes of open sets, with equivalence classes of open sets. And generally one can say that generally you have that when you have a positive element, and this positive element in the general C-star algebra will be always equivalent to A to the power 1 over n. And that will be Cuntz equivalent to that. And if you let n go to infinity, then this converges to the open support projection of this element A. This would be something in 2 star, the open support projection. And this can be actually, or this concept has been formalized in the 60s. Aikman defined the concept of an open projection. It's actually a good idea to think of the Cuntz semigroup as classes of open projection. WA as classes of open projection. Another picture would be to think of them as classes of hereditary subalgebras. Okay. And
then the relations is like what you have for projections?
That's right, yeah. You have then, well, you have this relation here. You can actually also make it, you can think of it as a relation inside here. There's a sort of equivalence relation, a Penny-Zito equivalence.
So A is less or equal than B in that sense, even only the corresponding projections in the projection sense. And A double star are.
Yeah, but you have to be a little bit careful what sort of partial isometries you're allowed to use then in the A double star.
So what kinds are you allowed to use?
You have to they have to satisfy some regularity, but they have to be some sort of multipliers of hereditary subfactors. This is a subtle condition because it's difficult to really formulate this relation here in terms of partial isometries in this A2 star. It's then difficult to find out which partial isometry you're allowed to use. But it is still heuristically a good picture we need to describe the Cuntz Semigroup term. Right. Okay, and the second example I want to just mention is that of stably finite algebras. The Cuntz Semigroup is really sort of made for these stably finite algebras, or for algebras which have traces. So if A is stably finite, that means whenever you have an isometry in the algebra, then that should be unitary in A and also in Mn. We talk about a unital algebra, and then we take also Mna, it's also a unital algebra. We want this sort of finiteness condition. Every isometry is actually unitary, and in that case, you can write down what this WA is. The WA in that case decomposes into the Murray-von-Neumann semigroup of projections together with purely positive elements. I think it's usually is an upper plus or sometimes a double plus. These are the purely positive elements. So this would be Murray-von-Neumann classes of projection. And this is the purely positive part, those elements which are not equivalent to a projection. So one can say that actually, in this case, for stably finite algebras, the Cuntz Semigroup contains all the information about K0, and this part actually contains information about the traces of your algebra, which sometimes unifies part of the K theory and traces. Okay, and then one last degenerate case. I should also say here, this object is already usually rather big. It's a large object, and there's a degenerate, and generally if you look at also the case of a commutative C star, you can see this, your Cuntz Semigroup will be a very big object in general. And there is the degenerate case, which is the purely infinite case. So if A is simple and purely infinite, that means whenever you take A and B in A plus without 0, then there exists an X such that A is equal to X star B, X. So any two elements actually in A are then Cuntz equivalent, as you can see. We can swap the rows on A and B here. Then we get that WA consists just of two elements, 0 and infinity. So in this moment, the Cuntz Semigroup degenerates to this two-point object and doesn't contain the information about AC gradient. So that's very little information. Okay. We just very quickly mention the connection between the Cuntz Semigroup and traces. So, Cuntz Semigroup and traces. If you have a trace on algebra A that extends chronologically to a trace on M infinity A just by tensoring it with your standard trace on M in infinity, okay, such a trace extends to, well, these open projections. Open projections. These support projections slash WA as follows. Then you can define tau of this PA as simply the limit of these A to the 1 over N. Yeah? N goes to infinity. Okay, and you can then, that gives you a functional on your Cuntz semigroup, so-called dimension function. You can formalize what dimension functions are, so where they behave. Basically, you axiomatize the behavior of these functions here. This gives you the notion of dimension functions, and then you can show that conversely, a dimension function in the Cuntz semigroup corresponds to a quasi-trace in the algebra. And for most algebras, actually, it's known that quasi-trace are always traces. So basically, traces on your algebra correspond to exactly dimension functions in the Cuntz semigroup. And in that sense, the Cuntz semigroup contains also the information about traces. WA contains information, all information of traces for the algebra. Okay, and one thing I want to mention is a technical condition here, which will feature later. That is a technical notion of strict comparison. So we say that A has strict comparison if the following holds. Tau of PA, I should say, yeah, which is tau of the Cuntz class, if you want, of this positive element A, smaller than tau PB. That implies that actually A is Cuntz below B for positive elements. A plus or. Okay, so in other words, the Cuntz order is determined by the trace order. That's what
For all traces or just
that's
one trace?
for all traces. Sorry, yes. For all to TA. That's called strict comparison. So for Neumann algebras, if you are in a factor or so, then it is well known that this is the case actually. But for C-star algebras, it's not clear actually. This condition's been, well, for a long time a bit mysterious, but it's turned out that this is important for classifiability. Actually, this condition seems to be equivalent to classifiability for algebras as a trace. Okay, feature discussion. Okay, so what's the role of the Cuntz semigroup in classification? Let me just quickly indicate that a little bit. The Cuntz semigroup and classification. An overview about classification. Well, it really can be seen in analogy of classification for Neumann algebras. So here on the one side we have for Neumann algebras. Okay, and on the other side we have C-star algebras. And here for Neumann algebras, it was early on Murray-von Neumann noticed that you can essentially reduce the study of von Neumann algebras to factors, simple von Neumann algebras. Here's not really such a clear reduction to simple C-star algebras, but classification should certainly start with the classification of simple C-star algebras. These factors decompose into different types. according to, well, basically the Murray-von-Neumann equivalence classes of projections, and that gives you the types. Type 1, 2, and 3. This is relatively easy decomposition into these types. And what's the corresponding object over here? That is really the Cuntz Semigroup, and I think that's what the motivation for Joachim Cuntz to define this Cuntz Semigroup. Find an analogy of the equivalence classes of projections to invariants. That's really the Cuntz Semigroup. And that gives you also a type decomposition into 1, 2, 3, but the decomposition is much more complicated, so this Cuntz Semigroup is much more structured than here on this side, and should feature in the classification of simple C-star algebras. So this was all in the 30s, and this developed from the 40s to the 70s or so. And then there was also in the 70s a classification of amenable factors by Harold and Kohn, which was first name Kohn, and Harold's contribution came in the 80s later. There was one case left over, and then here the corresponding program is the Elliott classification program. Which aims to classify amenable, that means nuclear, simple, separable, here is also separable people, simple separable C-star algebras by the Elliott invariant basically, yeah, one could say by K-theory traces, combination of the two, and that is the Elliott invariant. Elliott invariant. EA is just a pair consisting of K-theory traces in the position of the one in the K-naught group, the pairing between traces of K-naught. Okay, and there have been quite some developments here on the classification of these algebras. Let me just quickly give two results. There's a Phillips classification. Phillips classification of purely infinite such algebras. So if A and B are purely infinite, simple, nuclear, unital, then we don't really need that. Purely infinite, simple, nuclear, separable. These are Kirchner algebras. Then you can say that if A and B are KK equivalent, then they are going to be stable isomorphic regions of K, isomorphic to regions of K. there are refinements of that. You can actually say if there are KK equivalents and your KK equivalence between the two algebras is such that the position of the unit in K naught is mapped to the position of the unit in K naught here on this side, then that gives you an isomorphism. And the second part here uses a UCT if A and B satisfy UCT. And that means basically K theory determines KK theory, and K theories are when EA is equal to EB, then A and B isomorphic. And in this case, it simply means K theory, including the position of the unit in K naught. That's the end of invariant in this case, because there are no traces. And so that was around 95, and then recently there has been a theorem which is the endpoint of a long development. He uses in winter he proved a generalization of this result, really, which says that, at least on the second part, if A and B are simple separable nuclear unital and what else do we need? With UCT. And the so-called nuclear dimension of A and B, which is the topological dimension for C-star algebras, is finite, so for both of these we want that this is finite, then, and moreover, then EA equals to E implies that A and B are isomorphic. So they're classified if they satisfy this regularity condition of finite nuclear dimension. And you could, of course, think about why is that the right regularity condition, finite nuclear dimension. And it turns out that this seems to be a condition which is equivalent to a number of other conditions, which I just want to quickly mention. There is a conjecture which is, well, to quite an extent now established by Thompson Winter. That conjecture says that actually A is simple, nuclear, unital, separable. Then the following are equivalent, namely that this nuclear dimension, the nuc, which I think we discussed, it's, as I said, a topological dimension for C-star algebras based on covering dimension. The second condition is that A is absorbing the Young-Su algebra. A tensor Z is isomorphic to A. The Z is the Young-Su algebra. This is a slightly weird condition, but I think it was realized first that this is the right condition. And it's a bit explained by the history of the subject. For this Kirchberg-Phillips classification, the key result was that if you have a purely infinite nuclear simple C-star algebra, you tensor it with O infinity, then it is isomorphic to that algebra. So it absorbs O infinity. That was the key result. And therefore one looked at for similar objects for algebra with traces. And this is the Young-Su algebra. Place the similar hole here. And then comes up this funny condition for the Cuntz Semigroup, which we discussed before, namely A has different flavor, really. And it turns out that this is apparently, well, equivalent to these other two conditions. So this conjecture has been established in a number of cases. I should like proof here. So 1 to 2 to 3 is known, whereas 3 to 1 is known in good cases, known under restrictions on the trace space, and the restrictions are that you have, for instance, only finitely many extremal traces, or that the boundary of the trace simplex is compact. That's a typical condition you need here. Okay, so that's really the outstanding direction still, which is not known in all cases, but okay, in a number of cases it is known. Let me just write out a couple of little remarks here. Time-wise, how much time do we have? When did we start? I forgot.
About 25 minutes.
25 minutes. Okay. Okay. Right. Then let me just point out a couple of remarks here. So, first of all, this result here is a generalization of the previous one, because it is known that if A is a Kasparov algebra, then the nuclear dimension of A is finite. And then secondly, the second condition is necessary because it is known that E A tensor Z is EA for a simple nuclear C star, and therefore we need the second condition, that the exactly condition, if the Elliott program in its original form is true. And then the third remark I want to point out is there are counterexamples to the classification without this regularity. So there exist A and B simple nuclei with all the other conditions, such that the Elliott invariant of A and the Elliott invariant of B are the same, but they're not isomorphic. So this is an example due to Cuntz. However, in this case, WA is not the same as WB. So the Cuntz Semigroup actually can distinguish between these two algebras in Cuntz example. And therefore, it might be possible to extend this result here or generalize the Elliott program by just adding the Cuntz Semigroup as an extra invariant. So that gives you a direction of the classification program. By adding the Cuntz Semigroup, we might might be able to extend the current classification program. Okay, right. So what do I want to do now? With this background a little bit, I want to just point at two directions in the application of the Cuntz Semigroup. One is that we want to, I shouldn't erase this here. One is the attempt to introduce a bivariant Cuntz Semigroup and to use that in order to mimic this Kirchberg-Phillips classification. And the other one is to use Cuntz Semigroup techniques to show classifiability. So in the Kirchberg-Phillips classification, KK, in the first part actually, KK equivalence is more or less equivalent to stable isomorphism. without any UCT assumption. And it would be nice to have basically a generalization of this KK functor, which would work also for algebra with traces. And then you also want to use Cuntz Semigroup techniques to establish one of the three conditions for classifiability, namely the second one, which was strict comparison. Unfortunately, I wiped that off just now. Okay, so let me say something about bivariant Cuntz Semigroup, and how we want to define this. The basis for this is the following definition. We get an order zero map. These are the objects we want to use. So the linear map between C-star algebras from A to B, linear map, is called order zero if it preserves orthogonality. That is to say, if you take A1 and A2, which are orthogonal in A, meaning that all products are zero, also products with adjoint for them, or you can just work with positive elements. That's enough for us here. For positive elements, the product is zero. That will imply that phi A1 is orthogonal to phi A2, the product of those two should also be zero. Also multi-preserving maps. And then we introduce the completely positive order zero maps, CP per AB. These are just, well, the order zero maps from A to B, such that phi is completely positive. Okay, these are relatively close to homomorphisms. In the sense that this is essentially given by a homomorphism times a positive element commuting with the range of such a map. And why do we, okay, then we use these as a basis for our bivariant Cuntz Semigroup. So what we can introduce now, if we have such a map from A to B, we can introduce a sort of mimic the Cuntz order for those. So we can say, given phi and psi in CP per KB, we can say that phi is conjugate of psi if and only if there exists a sequence Bn such that Bn star psi A Bn tends to phi A, and that should be the case for all A and A. Okay. And then you also have the Cuntz equivalence. Phi is equivalent to psi, if and only if phi is Cuntz below psi, and psi is Cuntz below phi, just in the same way as before. Then you get an object. Then we find an object analogous in Cuntz Semigroup, just bivariant now. And so we define WAB now as simply this CP per A, and here we take the infinite matrices with values in B, and then we divide by this relation, and in the same way, a slightly different version of that analog of the CU here, which would be here CP per A, and here we have B tensor K, modulo the same relation. Okay, so this is how we would define the bivariant groups, or semigroups. These are semigroups just as before, and then we get that WCB is our usual Cuntz semigroup, and WWCB is CUB we cover that. That's just like in KK theory. You also have a product in the theory, just like in KK theory, given by composition. You could ask yourself, why do we use these order zero maps? We use order zero maps because order zero maps induce morphisms between Cuntz semigroups, contrary to completely positive maps. You could think of just taking completely positive maps and form such semigroups in this setting, but they don't really give you, and elements in there don't give you morphisms of the Cuntz semigroups, and they also don't induce maps between the traces. So why superb? Well, because such induce maps or morphisms of the Cuntz semigroups WA to WB, and then also traces on B with the traces on A, just by composition. Okay, as I said, you get actually a structure which is relatively similar to KK, although it is only, in some sense, an unstable, would correspond to something like an unstable version. Okay, and it turns out that then we get a classification, in a sense, using this. Namely, we get some time back, we can show that if A and B are WW equivalent, then actually A and B are stable isomorphic. And that, well, that actually, for that we don't even need simplicity or anything, nuclearity, so that is a very general result. And I should also say that the proof of that is much easier not comparable than Kirchberg-Phillips. And also corresponds to the fact that these bivariant semigroups are huge objects in general. They contain a lot of structured information. So that is not so surprising. And I should also say what the main point of Kirchberg-Phillips, or one of the technical points in Kirchberg-Phillips, is that when you have a general KK element which is given by pairs of morphisms in the Cuntz picture, then you can replace it by one which is given by a single map. And if you use this step is a difficult step, so to speak. Once you have a single map, then you only have to show that this KK equivalence is actually an isomorphism. Whereas we have already a single map, and we only need to show is that you can turn it into an isomorphism. So our result is not comparable in depth to Kirchberg-Phillips result, but at least points in maybe the right direction.
So how easy is it to determine whether two algebras are equivalent in a sense?
That's in a sense much harder to because you don't know anything about these semigroups.
Right.
You have no technology. So what we perhaps need to do is replace this WW by some sort of how can I say, Grothendieck group. You have to mimic the construction of KK out of pairs of morphisms, and then we get maybe tools to determine this sort of K theory. But then we would get a group in this way. We would need to develop techniques to determine this group, and then this might be an applicable result.
I just ask, if you drop this assumption of order zero in your definition, would you still get CU of B if you plug in C in the first particle?
If you just, order zero, in that case, you would still get it, because you see, if you take a completely positive map from C into, then you have just a positive element, right?
But then shouldn't you also get, I mean, the composition product should also still work, right?
Yeah, but it doesn't preserve the classes anymore. In general, so to speak. If you compose with a completely positive map, it's not so clear that the completely positive preserves the class, the Cuntz class. That's the problem here.
You see, there is
You
no
don't
more-
necessarily map classes on classes.
There is no more product.
Mhm. So you need some sort of weak form of multiplicativity to get the preservation of classes. That's the problem. Okay, right. So that was one thing I wanted to mention. We have a couple of other results about this Bivariant and Semigroup, but I just wanted to point this one out. The next thing I wanted to point out is that this is a different thing, namely it's the attempt to use Cuntz Semigroup techniques in order to establish classifiability for a class of algebras, namely for cross products. And that's something more recent. This Bivariant stuff is something I've done a while ago, and this dynamical Cuntz Semigroup technique was the more recent work in OS. Okay. Dynamical Cuntz Semigroup. Okay. So here we want to basically show the first condition in the Towns-Winter condition. Towns-Winter conjecture. We want to establish classifiability by showing straight comparison. So the goal here is show straight comparison / classifiability across products. Via Cuntz Semigroup. Okay, and so the setting is here the following. Suppose we have G acting on a compact metric space, so here we have G is an amenable group, amenable and countable group, and X is compact metric space. Okay, and the action alpha here is a minimum of free action. Okay, and we want to consider the cross products, Cx cross product T under the action alpha. This is a simple, nuclear C-star algebra. It satisfies also the UCT. That's the result by 2. Showed that groupoid algebras of this type, they always satisfy the UCT. And moreover, we also know what the traces are. The traces on this, they correspond to the invariant probability measures. Okay, but at least we can write them down. It doesn't mean that we know what they actually are in concrete examples. And the K-theory, well, that in some cases can maybe be attacked via the long-run conjecture. Okay, so there are also methods sometimes to determine K-theory of these examples. Okay, so are these C-star algebras classifiable? Are they covered by the results and the classification theory? And then we need to show classifiability. So is Cx classifiable? And then also what we are interested in, what is actually the Cuntz Semigroup of this? These two questions we want to address. And the classifiability you can approach in different ways. You can, for instance, try and show finiteness of nuclear dimension. That's basically the Rockling dimension method. Just quickly mention, there's the Rockling dimension method for classifiability. So there's a theorem by Saho myself from not too long ago, where we show that if G is finitely generated, nilpotent, and we also have that the dimension of X is finite, or the covering dimension of our compact space is finite, then in this situation, it follows that the nuclear dimension of this cross product is actually finite. Okay, and the method for this, I haven't written this down, which we establish actually that in this situation, this group has satisfies some asymptotic finite dimensionality. So you need actually the asymptotic dimension of this group is finite. That's automatic for those groups. And moreover, the Rockling dimension, certain dimensions of your actions, the Rockling dimension of such an action is also always finite, and then this combined gives you that the nuclear dimension of this cross product is finite. That means it's classifiable. It's classifiable. Okay, but this method has limits, the limitation being that this G has to be finite dimensional, so that the asymptotic dimension of this has to be finite. I also should say this method still has some mileage, so I'm sure there are some further generalizations of that. We use here visually finiteness of the group. I think that can be actually removed. And also the class of groups, so this is the case, can be pushed beyond nilpotent groups, but this finite dimensionality for the group, asymptotic dimension being finite, I think that cannot be removed. That seems to be a stumbling block here. So what we are interested here is basically different directions, different approach to the classifiability here would be using the so-called dynamical Cuntz Semigroup. We call the dynamical Cuntz Semigroup, and to show regularity conditions for that, use that in order to establish regularity for the Cuntz Semigroup, strict comparison, and then obtain classifiability. What's the basis of that? The basis of the dynamical Cuntz Semigroup is you start with classes of tuples. Basically, consider classes, equivalence classes of tuples. U1 up to UN, where these UI are open sets, and you have a sum operation, U1 up to UN plus V1 to Vn. It's just concatenation, U1 UN V1 Vn. And then you define an order for these tuples as follows. This is G below a tuple V1 up to Vn if there exists if for all ki in ui compact, there exists now wijk in vj open and pairwise disjoint, and moreover the mean sets, or not necessarily partition, you can cut out open sets in there. Okay, and then you can take these open sets, which you find also here, there exists also Gij in G, such that the Ki's are covered by Gij, Wij, and here we take the union of the J and K. The meaning of this is simply the following. Think of these here as subset of X, being also subset of X. We must be able to cut out open pairwise disjoint sets in here, shuffle them all around, cover everything here. That's what it means. Particularly an invariant measure, the measure of all those here will be bigger than the measure of those. Okay, so this is this dynamical Cuntz Semigroup. And then, okay, we define, of course, equivalence, G equivalence, by definition to be this and this. Take it together, just as before, and that leads to a dynamical Cuntz Semigroup, G acting on X here, as classes of these U1 up to UN. Okay, and there's also a natural map now from this dynamical Cuntz Semigroup into the Cuntz Semigroup of the corresponder. What you do here is you take a tuple U1 up to UN and you map this to, take a class of that, to the following. You take the diagonal matrix F1 up to Fn, and the class of that, and here these Fi are positive functions such that the open support of Fi is just U. That's what you do. That gives you a map which would be a morphism. It's not clear that it's injective. Is the equivalence you have here the same as the equivalence here? Okay, and what we want, of course, is that the map has a large range. Ideally, it should be everything. And in fact, it turns out that this is often everything. So, what we obtain is, maybe before I write it down, I also have a version of the strict comparison in this setting, a dynamical strict comparison. And how is that defined? I'll just quickly say, so yeah, the definition of strict comparison. In this dynamical Cuntz Semigroup, that would be the following. You would say, suppose the measure of a tuple, what's the measure of a tuple? If you take an invariant measure, you just take the sum of all the measures. If that's smaller than the measure of Vj, for all mu invariant probability measures, then that should imply that this tuple U1 UN is below G below U1 up to Vm. Okay, that would be the version of strict comparison in this dynamical Semigroup. And then it turns out that it turns out that actually under certain assumptions, if alpha admits a certain dropping power decomposition, then we actually get strict comparison as strict comparison. And moreover, we know that WGX is an embedding and it's an ISO. In good cases, well, I should say dense, under the same sort of assumption as we have for the regularity condition, strict comparison implying a finite nuclear dimension. We mentioned in the beginning, if it's a trace simplex has compact boundary under good conditions. Okay, and that would give us then classifiability actually by a Cuntz Semigroup method in this situation. We obtain classifiability. And this Rocklin-Tower condition here is generic, actually, has been shown by David Kerr and some other authors, largely other authors. And they, I should also say, have recently shown that this condition implies Z-stability directly, so also classification. But this is an alternative approach to classifiability using the Cuntz Semigroup. Okay, I stop here. Thank you very much. Thank you.
Questions or comments for the speaker? Thank the speaker again.